it turns out that the equation 3.10 here actually tells us something more about the convergence. And now let's dig a little bit more into this. First, as in the book, let's call this inequality 3.5. 3.5 together with 3.10 give us the following. So first, let's copy those equations down in here. 3.5 says we have the inequalities 1 equal to Q0, which is less than or equal to Q1, less than or equal to Q2, all the way. And 3.10 tells us that we have this convergence of infinite continued fractions. And now we make the following claim. Claim that U is squeezed between the following sequences. Above, by all the odd terms, P sub 2m plus 1 divided by Q sub 2m plus 1. And this is less than or equal to all the way to P sub 3 over Q sub 3, which is less than P sub 1 over Q sub 1. U is also bounded below by all the even terms. P sub 2n divided by Q sub 2n all the way to P2 divided by Q2. This is greater than P0 divided by Q0. Okay, so why this is true? Let's quickly check this. Indeed, P sub 2m plus 1 divided by Q sub 2m plus 1, because of our formula here for P sub n over Q sub n, by this telescoping sum, this is equal to P sub 2m minus 1 divided by Q sub 2m minus 1 plus, so be careful at this point, this is negative 1 raised to the power 2m plus 1 times 1 over Q sub 2m minus 1 times Q sub 2m. You can also look at here, plus one more term, negative 2 raised to the power 2m plus 2 times 1 over Q sub 2m times Q sub 2m plus 1. Okay, now comparing this guy with this guy, do you see which one is bigger? So now let's check this. This is negative 1. This is positive 1. But noticing that this Q sub n is ascending, is increasing. So this denominator is smaller than this denominator. So this fraction is bigger than this fraction. So what we get here is the right hand side is less than P sub 2m minus 1 divided by Q sub 2m minus 1. So on the right hand side of U, so those sequences are really increasing. I mean, this odd numbered subsequence is decreasing as this index goes to infinity. What I mean is that this odd numbered subsequence is really decreasing with indices. And similarly, you can prove that the even numbered subsequence is increasing with the index. So this verifies the claim. So you can easily do the even numbered case. And at the same time, so those subsequences all converge to you, because the sequence itself converges to you. And now here we give a definition. We say that this infinite continued fraction is sub 0 is 1 is the continued fraction expansion for u. And this name seems to suggest that the continued fraction expansion seems to be unique, and it always exists. And we will make this more rigorous in the lemmas below. Now let me introduce some more interesting results concerning the continued fractions. Those rational numbers p sub n over q sub n also have names. The rationals p sub n over q sub n are called convergence of the continued fraction for u. And actually, it turns out that they provide very rapid rational approximations to u. And in fact, what you can see from here is that u minus p sub n over q sub n is equal to this convergent sequence. Actually, this is just the tail of that infinite sum. And now you take the absolute value of both sides. When you take the absolute value, you get the right hand side is just 1 over q sub n times q sub n plus 1 minus 1 over q sub n plus 1 times q sub n plus 2, etc., etc. And because those q sub n's are increasing, this telescoping sum is actually bounded by its first term, the biggest term. So this is strictly less than 1 over q sub n plus 1 by advanced calculus. Okay. Now let's further simplify this. But we know that this guy is less than or equal to 1 over q sub n squared, because q sub n is increasing with n. So this is true for all n greater or equal to 1. And remember, in our lemma 3.1, this quotient is reduced, namely p sub n and q sub n are co-prime. And this inequality holds for all n greater or equal to 1. This tells you when you choose n bigger and bigger, you will get infinitely many different p sub n over q sub n's. And this can be summarized into the following theorem. Okay, now if you accept the fact that with every irrational number, u has a continued fraction expansion u equal to a0, a1, all the way through a sub n, say a continued fraction expansion starting from a0, then we have some very interesting results. So first, look at this inequality. We know from the above lemma 3.1 that this p sub n over q sub n is this finite continued fraction. And this guy converges to this irrational number u. And at the same time, you know by the lemma 3.1 that p sub n and q sub n are coprime. So as n goes to infinity, this fraction will change, and the denominator will get bigger and bigger. And you will get infinitely many those fractions satisfying this inequality. And this can be summarized into the following theorem. This theorem says that u be an irrational number then there exists infinitely many rational numbers p over q with pq coprime such that the absolute value of u minus p over q is bounded by 1 over q squared. Although what we just proved is the case when u is positive, so this theorem is also true for when u is negative, because you can always change the sign of u and p over q, so that you, after you take the absolute value, you still get the same thing. And this theorem is not any theorem. This is a famous theorem due to Dirichlet. So Dirichlet has many theorems, and this is the one on the defining approximation.